Welcome back. In this video, I'm going to outline a general algorithm for recursive descent parsing. Before I dive into the details of the recursive descent parsing algorithm, let me just define a couple of small things that we're going to use throughout this video. Token is going to be a type, and we're going to be writing code, and so token will be a type of all the tokens. And the particular tokens that we'll use in the example are things like int open, paren, close paren, plus, and times. And so token is a type, and these things are instances, values of that type. And then we're going to need a global variable called next that points to the next token in the input stream. And if you recall from the previous video, we used a big arrow to point into the input to indicate our current position. The global variable next is going to play the same role in our code. So let's begin. The first thing we're going to do is define a number of Boolean functions. And one function we have to define is one that matches a given token in the input. So how does this work? Well, it takes as argument a token, okay, and this is of type token again, and then it just checks whether that matches what's currently pointed to in the input stream. So is TOK equal to the thing pointed by next? And notice that as a side effect, we increment the next pointer. And what's returned then is a Boolean. This is either true or false. So yes, the token that we passed in matches the input, or no, it doesn't. And again, just to stress this, notice that the next pointer is incremented regardless of whether the match succeeded or failed. Now, another thing we need to check for a match of is the nth production of S. So this is a particular production of a particular non-terminal S. And we'll denote that by a function that returns a Boolean, and it's written as S sub n. So this is a function that only checks for the success of one production of S. And I won't write out the code for that now. We'll see that in a minute. And then we're going to need another function that tries all the productions of S. So this one is going to be called just S with no subscript, And so what this one will succeed if any production of S can match the input. All right, so we're going to have two classes of functions for each non-terminal. One class where there's one function per production, and it checks just whether that production can match the input, and then one that combines all the productions for that particular non-terminal together and checks whether any of them can match the input. Okay, that's the general plan. Now let's see how this works for some specific productions. And we'll just use the same grammar that we used in the last video. The first production of that grammar is E goes to T. And now what we want to do is we want to write the functions that are needed to decide whether this production matches some input. And this one happens to be simplicity itself, and it's easy to see why. So first of all, we're writing the function E1. This is the function that deals with the first production for E and returns true only if this production succeeds in matching some input. Well, how would this production match any input? Well, it could only match some input if some production of T matches the input. And we have a name for that function. That's the function T, which tries all the different productions for T. So E1 succeeds, returns true, exactly when T succeeds, returns true. And that's all there is to this first production. For the second production, we have a little more work to do. Now E will succeed if T plus E can match some of the input. And how does that work? Well, first, T has to match some of the input, so some production of T has to match a portion of the input. And after that, we have to find a plus in the input following whatever T matched. And if plus matches, then some production for E has to match some portion of the input. And notice the use of the short-circuiting double AND here. So this is actually important. We're exploiting the semantics of double AND in C and C++, which evaluates the arguments to the double AND in left to right order. So first, T will execute, and notice that T has embedded within it side effects on the pointer into the input. So it's incrementing the next pointer, and it increments it exactly however far T makes it. So whatever T manages to match, the next pointer will advance that far, and when this function returns, it's left pointing to the next terminal that T did not match, and that needs to be a plus, and the call to term will increment the next pointer again, which is exactly where E should pick up. And whatever E can match, it will increment the next pointer just beyond that, so that the rest of the grammar outside of this particular call can match it. And then notice that this particular function is called E2 because this is the function for the second production for E. Well, we have one more thing to deal with for E, and that is the function E itself. We need to write the function that will match any alternative for E. And since there's only these two productions, it just has to match one of these two productions. And this is where the backtracking is dealt with. Now, the only bit of state that we have to worry about in the backtracking is this next pointer. So that needs to be restored if we ever have to undo our decisions. And so the way we accomplish that is we just have a local variable to this function called save that records the position of the next pointer before we do anything. So before we try to match any input, we just remember where the next pointer started when this function was called. Okay? And now to do the alternative matching, we first try E1 and we see if it succeeds. And if it doesn't succeed, well, actually, let's do the succeeds case first. If this succeeds, if this returns true, then the semantics of double OR here means we don't evaluate E2. So this will not be evaluated. The second component here will not be evaluated if E1 returns true. It'll short circuit because it knows that it's going to be true no matter what, and it'll just stop there. And notice that whatever side effects E1 has on the next pointer will be retained, and we'll remember, and when we return true, the next pointer will be left pointing to the next piece of unconsumed input. Now let's consider what happens if E1 returns false. Well, if E1 returns false, well then the only way this OR can be true is if the second component is true. And what's the first thing we do? The first thing we do is restore the next pointer, okay, before we try E2. And if E2 returns true, then the whole thing returns true, and the E function succeeds. If the E function fails, well, then we're out of alternatives for E, and the failure is going to be returned to the next higher level production in our derivation, and it will have to backtrack and try another alternative. Now finally, what about this particular statement, next equals save here? Well, this is not strictly needed. Notice that here we save the next pointer in the save variable, and then the very first thing we do is we copy it back over to next again. This is just for uniformity to make all the productions look the same. But since this is the very first production, we actually don't need this assignment statement if we don't want to have it. So now let's turn our attention to the non-terminal t. There are three productions. The first one is that t goes to int, and that's a simple one to write. We just have to match the terminal int. So the next thing in the input has to be an integer, and if it is, then T1 succeeds. T2 is slightly more complex. That's the production int times t. T goes to int times t. So we have to match an int in the input, followed by a times, followed by something that matches any production of t. The third production is t goes to open paren e close paren. So what has to happen, we have to match an open paren first, and then something that matches one of the productions of e, so we call the function e there, and then finally a close paren. And then putting all three of these together in the function t that tries all three alternatives, we just have exactly the same structure we had for e. So we save the current input pointer, and then we try the alternatives T1, T2, and T3 in order, and at each step we restore the input pointer before we try the next alternative. To start the parser up, we have to initialize the next pointer to point to the first token in the input stream, and we have to invoke the function that matches anything derivable from the start symbol. So in this case, that's just the function e. And recursive descent parsers are really easy to implement by hand. In fact, people often do implement them by hand in just following the discipline that I showed on the previous slides. To wrap up this video, let's work through a complete example. So here's our grammar, and here is all the code for the recursive descent parser for this grammar, and here is the input that we'll be looking at. And we're going to just mark the next pointer, pointing to the initial token of the input. All right, and I'll also draw the parse tree that we're constructing at the same time. So we begin by invoking the start symbol. So we're going to be trying to derive something from E. And the first thing we'll do is we'll try the first production. So we'll try E1. And what does E1 do? E1 is going to try T. It's going to try to derive something from T. So our possible parse tree looks like this. And so we invoke T. And what is T going to do? It's going to try all three productions for T in order. And so it's going to call T1, and we'll see that T1 is going to fail because it's going to try an int. And I won't put it in the parse tree since it isn't going to work, but the int is not going to match the open paren. So that's going to return false, which will cause us to backtrack. It'll reset the input pointer, okay, and to the beginning of the string, and then it'll try T2. And T2 is also going to ask, well, is the input pointer equal to an int? And recall that the term function here always increments the input pointer. So in fact, this pointer is going to move over one token, but this is going to return false because int doesn't match open paren. So we'll come back here. The input pointer will be restored back to the beginning of the string, and then it's going to try the alternative T3. Now when we finally get to T3, something good is going to happen. The first thing it's going to do is going to ask, is the first thing in the input an open paren? And in fact it is. And so the input pointer will advance to point to the int. And then it's going to try to match something derivable from E. So now we have our first recursive call to E. We're back here at E, and it's going to try E1 first and then E2. And so it calls E1, and E1 will only match something if it can match T. Okay, so this is we're down here inside of E now, and then we're going to call T. And what's T going to do? Well, it's going to try all three productions for T in order, the first one of which happens to be the single token int, and that is going to match. It's going to call term int. T1 is calling term int, and that matches the next token in the input stream. So we're happy about that. The input pointer advances again. And now we return through all these levels of calls. T1 succeeds, which means that T succeeds, which means that E succeeds. Okay, and now we're back here in the production for T3, and we're going to ask, well, is the next thing that we see in the input a closed paren? And indeed, it is. And so a closed paren will be recorded. And now T3 will succeed, which means that T succeeds, this T succeeds. And finally, we return to the root call, E, and that returns true, which means that the parse succeeded. That plus the fact that we are now at the end of the input. There's no more input to consume, and we've returned from the start symbol with true, and so we have successfully parsed the input string.